In this hour, we're going to focus on thermochemistry and getting a good understanding of what is meant by this section of the course. This part always comes up on your Leaving Certificate Chemistry exam, so it's a given question. It's always in question 6 of the exam, and it's always kind of mingled and intertwined with fuels as well. However, in this hour, we're just going to focus on the thermochemistry aspect of the question. In the first part of the video, we're going to be able to define what thermochemistry is. You're going to revise and be able to define what a physical, chemical, and exothermic reaction is. You're going to be able to provide an example of an exothermic reaction in everyday life, and you're going to be able to define and give an example of an endothermic reaction in everyday life too.
First thing you need to know is, well, what is thermochemistry? And all thermochemistry is it's the study of heat changes that accompany a chemical reaction. It can also be referred to as chemical thermodynamics, and I suppose the term chemical thermodynamics has its origin in the study of heat engines, where heat and movement gave rise to the name thermodynamics.
Changes of state also result in heat changes. So, for example, if you put a volatile liquid such as ether or maybe even cyclohexane on the back of your hand, you'll feel a drop in temperature. This is because the heat energy needed to change the liquid to a gas comes from your hand. But for example, a burn from steam can be more harmful than a burn from boiling water. And that's because the hot steam condenses on your skin and the excess energy of the gaseous molecules is lost. And unfortunately, in the form of heat when they become a liquid. And this heat can cause severe burning. And that's why they always say you have to be really careful of steam burns as opposed to even maybe liquid burns. So changes of state are not classified as exothermic or endothermic reactions. They're merely physical changes rather than chemical reactions, but there's also just to be aware that there's a heat change present in those ones as well. We'll really quickly just revise chemical and physical changes just to make sure you know what they are. You should know them from junior cycle, but it's just to make sure that any misconceptions you have, we change and fix at the moment. In junior cycle, you would have learned a lot about physical changes, and it's just the change of a substance from one state into another. In a physical change, no new substance is being formed. So, for example, when liquid water is cooled, it changes into a solid, which is just known as ice. The particles of the water do not change into particles of something else. They are still water molecules. When heat energy is added to frozen water, it turns back into liquid water. This is another characteristic of a physical change. It is usually easily to reverse it. Physical changes happen all around us. So even if you think of easy things that happen every day, like jelly setting in the fridge, or if you're chopping onions, and if you're using a blender maybe to make a smoothie, they're all examples of physical changes. Now, you might argue that it'd be quite difficult to make a strawberry look like a strawberry again if you have physically changed it in a blender. But that's why we say that physical changes are usually easy to reverse. You should also know that there's 4 main changes of state. So we've melting, boiling, freezing, condensing. You probably know sublimating as well, so going from a solid to a gas. A chemical change is the second type of change that can happen in chemistry. Chemical changes are also known as chemical reactions. There are many examples of chemical reactions that occur in everyday life. I suppose the easiest to think of is when an open jar of nails is left outside, the nails will turn into kind of crumbling rust. And that's an example of a reaction between air and the iron. Other examples of chemical reactions are when you cook scrambled eggs or when you burn toast. There's loads happening in our body all of the time. For example, when you digest your breakfast or when your muscle cells release the energy from the digested food, chemical reactions occur. One of the main things about a chemical reaction is when it happens, a completely new substance is formed. So if we think about the rusty nails again, it doesn't just look different. The rusted iron becomes flaky and brittle as well and turns into something completely different to the original iron metal that would have been there at the start. So by reacting with the oxygen, the iron has become a new compound, and that compound is iron oxide. Another thing to note about chemical changes is they are not easily reversed at all. So for example, baking a cake in an oven is a chemical reaction. Once you put the cake mixture into the oven for perhaps maybe an hour, the flour, the eggs, the butter, they go through a chemical change or a chemical reaction, and something new is formed, and that's definitely not flour, and you wouldn't be able to get the eggs back because it's now changed into a cake. Chemical reactions as well involve an energy change, And this is obvious in some drastic chemical reactions, such as maybe like exploding fireworks, um, because you can see things like light, sound, and heat, all different forms of energy. However, the main thing to note here is there's three signs of a chemical reaction. So first of all, we could have something like a gas being produced. A color change could happen, or maybe a cloudiness or a precipitate is formed. And you'll probably remember them from when you were doing the test for anions. And as well, we could also have heat, light, sound, or electricity being produced. The main thing to note though is they're only indications that a chemical reaction may have occurred. To be more certain, further investigations usually have to be done. But the main thing is that you now know the difference between a physical and a chemical change. Now that we've gone over a chemical and a physical change, we need to be certain on what an exothermic and endothermic reaction is. An exothermic reaction and an endothermic reaction, you would have looked at a junior cycle, but now you're kind of looking at it through a more sophisticated lens. Before you did thermochemistry in school, you probably would have looked at fuels. Now, one of the most important properties of a fuel is that it burns in air. If you made ethene and ethine, which are one of the mandatory experiments on leaving cert chemistry, you would have known the combustion reaction that occurs with them. Now, when you combust them, you would have got heat out, and any chemical reaction that produces heat is an exothermic reaction. The main thing to note that all combustion reactions are exothermic reactions. So the combustion of ethene and ethine, exothermic. Even the burning of food inside of our body, that supplies us with energy, that would be an exothermic reaction as well. However, not all chemical reactions give out heat. In some cases, a drop in temperature is observed when a chemical reaction occurs, and in this case, heat has been taken in from the surroundings. You'll notice a drop in temperature. For example, if you hold maybe a beaker of water at room temperature and then add some ammonium chloride, and your hands will get much colder. And the reason why is because the heat has been taken from your hands, and this reaction is referred to as an endothermic reaction. And all you need to know is that an endothermic reaction is one that takes in heat. An example of an everyday endothermic reaction would be perhaps maybe sorbet. When you put sorbet into your mouth gets much colder, and it's because it's reacting with your mouth and taking heat from your mouth into it. Okay, so we've kind of had the introduction of the chapter now. It's kind of just revising what you would have known at junior cycle, making sure to iron out any misconceptions that you might have. But you should now be able to define thermochemistry. It's just the study of heat changes, what a physical change is, what a chemical change is, what an exothermic reaction is, provide a few examples of them, define what an endothermic reaction is, and provide a few examples of them too. In the next few slides, we're going to start looking at leaving cert thermochemistry. And in particular, what we're going to focus on is we're going to focus on defining the heat of reaction, recalling the symbol for it, stating the units for it, and then defining what a thermochemical equation is. Okay, the first thing we need to know is the definition for heat of reaction, and that is just the heat change when the number of moles of reactants indicated in the balanced equation for the reaction completely react. Now, the symbol for heat of reaction is delta H, and the units is kilojoules per mole. And if you keep that in mind as we're going through the next section. If we have a negative value for delta H, that means it's an exothermic reaction. And if we have a positive value for delta H, that means that it is an endothermic reaction. So if we take an example here really quickly, we can look at hydrogen burning in air. So hydrogen is H2, and hydrogen is always going to be in the gaseous form when it's being burnt. Then we're going to react it with oxygen, which is a gas as well. And what's going to happen then is it's going to form water, which is H2O. And again, in this case, it will be the gaseous form. Now, if we want to figure out the heat of the reaction, or the delta H, that's equal to 242 kilojoules per mole. And again, you don't ever need to know this, but it'll be given to you in the exam. So what happens is they write out the chemical equation, and then beside it they write the delta H, which shows us whether, first of all, it's exothermic or endothermic, and then the value. The bigger the value, the more heat either taken in or given out. The kJ stands for kilojoules, and the SI unit for energy now is joules. But since 1 joule of heat energy is rather small, heat changes when molar quantities react are normally measured in kilojoules, just because it means that it's smaller numbers that we're dealing with. The mole to the power of -1, or per mole, in the equation that we have here, indicates that we're working with moles rather than molecules. So in this equation here, the heat measured refers to 1 mole of the H2 reacting with half a mole of O2 to form 1 mole of water, which is H2O. And the delta H value is commonly referred to as the heat of reaction, and that's where we got the definition on the last slide from. If the numbers of moles in the balance equation are changed, then the heat of the reaction also changes. So for example, if we burn twice the amount of moles of hydrogen in this case, we're going to get double the amount of heat. So the heat of reaction will double. It's really important to note that when we're dealing with heat changes, it's so important to give the physical states of the reactants and products. And the reason why is because changing the physical states of either the reactants or the product can alter the value of delta H, or the heat of reaction. So for example, the heat of reaction, if we had the previous example where we had gaseous hydrogen, if we had changed that to liquid hydrogen, the heat of reaction would have changed. A thermochemical equation then is an equation that's balanced. The value of delta H is shown and must be written, and the physical states of the reactants and products are given as well. So it's basically just a normal equation with just 3 criteria. So it must be balanced, it must have the value of delta H, and it must also have the physical state of the reactants. Okay, so just kind of take and check what we've done so far. In the last few slides, we've defined the heat of reaction. It's just the heat change when the number of moles of reactants indicated in the balance equation for a reaction will react completely. The symbol for heat of reaction is the delta H. The units for it are kilojoules per mole. And then a thermochemical equation is just an equation, but it has 3 criteria. It must be balanced, the value of delta H must be written, and the physical states of the reactants products must be given too. The next section of this video then, we're going to look at heat of combustion. We're going to discuss the combustion of hydrocarbons. We're going to recall the use of a bomb calorimeter. We're going to recall the heats of combustion for different fuels. We're going to define the kilogram calorific value, and we're going to recall the use of the kilogram calorific values. Now, the term heat of reaction is the general term used for any type of chemical reaction. However, in some cases, a different term is used to indicate the particular type of chemical reaction being considered. As already stated, a reaction in which a substance is burned is called a combustion reaction. So the heat of combustion then is just the heat change when 1 mole of a substance is completely burned in excess oxygen. Now there's 2 key parts to this definition. The first one is 1 mole, and you have to make sure you say 1 mole, and you have to make sure you say completely burned in excess, and excess being the key term there. So there's kind of 2 key terms. The first one is 1 mole, and the second one is excess oxygen. And in the next 2 slides, I'm going to explain why they're so important. The phrase completely burned in excess oxygen is important in the definition of heat of combustion. This is because some elements have more than one oxide. So for example, if we see there carbon, it's reacting with oxygen to form carbon monoxide. However, that value of delta H is not the heat of combustion of carbon, since complete combustion of carbon in excess oxygen forms carbon dioxide and not carbon monoxide. So the delta H value there is minus 111 kilojoules per mole. So it's an exothermic reaction, it's giving out heat. However, when we completely burn it in excess oxygen, we form carbon dioxide, and that has an exothermic value of 394 kilojoules per mole. And as you can see, there's a huge difference. So it's really important that we always have completely burned in excess oxygen, because if it's not completely burned, it mightn't kind of, I suppose, create the products that we want. The other important phrase in the definition of heat of combustion is 1 mole. If you consider the thermochemical equation used to describe what happens when butane from a gas cylinder is burned when using a cooker gas, the delta H value you get there is minus 5754 kilojoules per mole. So anyway, we know it's exothermic, but we would have known that anyway because combustion is always exothermic. However, if you look here, it doesn't have 1 in front of the butane, so it's not 1 mole. And the reason why it's not the heat of combustion is because by the definition, the heat of combustion involves 1 mole of substance being burned. So therefore, the heat of combustion is really that 5754 kilojoules per mole divided by 2. And it can be represented by the thermochemical equation, which we have at the bottom of the screen here. And that gives a delta H value of minus 2877 kilojoules per mole. So the reason why 1 mole is important is because if we didn't specify that it had to be 1 mole, well then we could just do 10 moles and we get like 10 times the amount of heat. But if we want to compare the heats of combustion, it's important that they're all compared with the same amount. So if you have, for example, 6 moles of butane, you want to compare that with 6 moles of propane. Now, that's why we say that 1 mole is an SX. We always want to refer to or compare them with 1 mole. Okay, now we've talked about what heat of combustion is and the importance of the definition. You need to know that heats of combustion are accurately measured using an instrument called a bomb calorimeter. Now, a calorimeter itself is any container used for the determination of heat changes. And the name comes from the old unit of heat, which is the calorie. And 1 calorie is just 4.18 joules. Okay, so as I've said in the previous slide, the heat of combustion are accurately measured using an instrument called the bomb calorimeter. Now, a calorimeter again is any container used for determining the heat changes. And a bomb calorimeter consists of a small steel container, which is known as the bomb, which you can see there in the picture, and loads of various other items. You don't really need to know anything about how it's used or how it's worked in terms of the equipment. We just need to know that it's the heat of combustions are measured using the bomb calorimeter and how you would go about using it. And in the next slide, I go through the steps involved in using the bomb calorimeter. Anytime you use a bomb calorimeter, you're going to follow the same steps, and they can be summarized really, really shortly. So a known mass of a substance whose heat of combustion is being measured is placed into the crucible inside the bomb. Then what happens is the bomb is filled with oxygen under pressure. So the oxygen therefore is in excess to make sure that the substance will be completely burned in oxygen. Then the bomb is placed in a known quantity of water contained in the calorimeter, and the substance is ignited electrically using the ignition coil of wire. After that then, the rise in temperature of the water is measured, and the heat produced is calculated using the formula heat produced equals mass times specific heat capacity multiplied by the rise in temperature. I'll also explain that equation in much more detail as we go on.
This picture here summarizes the steps that we looked at in the last slide. So first of all, we can see here a known mass of a substance whose heat of combustion is being measured is placed in the crucible inside the bomb. The bomb is the thing I'm circling here, and the crucible you can see is just like the little bowl. The bomb is filled with excess oxygen under pressure. And we can see here the oxygen will be inside here, and it's in excess, it's under pressure, and again it's in excess to make sure the substance will be completely burned in excess oxygen. The bomb is placed in a known quantity of water contained in the calorimeter, and we have that here. Here's the known amount of water. After that, then the substance is ignited electrically using an ignition coil of wire, and we can see them here. So the electrical leads to ignite the sample. The rise in temperature of the water is measured, and the heat produced is calculated using the formula, which I'm going to go through again on the next slide. And the heat produced when 1 mole of the substance is completely burned in oxygen is then calculated. So you can see here the rise in temperature is taken from here, and again it's the rise of temperature from the water that they're taking, not from the actual bomb itself. It's the heat that's been given out by the bomb for the water to be heated up. Now, this is the equation that you'd use to calculate the heat of combustion. So it's the heat produced is equal to the mass times the specific heat capacity multiplied by the rise in temperature. Now, the specific heat capacity will always be given to you in your exam. The rise in temperature, they'll have to give you either the starting temperature, the finishing temperature, or indeed just the rise in temperature. And then they might ask you to calculate the mass. However, don't worry about this equation too much. When you're doing the mandatory experiment where you're looking at determining the heat of reaction of hydrochloric acid and sodium hydroxide, you'll be looking at detail into this equation. So although we kind of need to know when we're talking about the bomb calorimeter, we don't really use it until we're looking at that mandatory experiment. This table here gives you a few examples of fuels and their heats of combustions, and these are the types of fuels that you'd be talking about throughout the course in chemistry. So as you can see here, I suppose the most efficient, or the one that gives out the most heat when 1 mole of it is burned in excess oxygen, is ethane. Hydrogen there as well. You can see ethanol, methane, and carbon too. You'll never need to know these values off by heart. However, they could put them on the exam, so it's just making sure that you've seen them before, that you don't freak out if they're given to you on an exam. The next thing you need to be comfortable with and confident with is the kilogram calorific value. And basically, in some cases, chemists wish to measure the heat given out by a fuel in terms of mass of a fuel rather than the number of moles. So, for example, if you look at the side of a cornflakes box, you'll find that 100 grams of cornflakes provides about 1,550 kilojoules of energy. Now, that value was obtained using the bomb calorimeter. And bomb calorimeters are also used to compare the efficiencies of various fuels, to see if a fuel is of good quality in terms of heat obtained from a certain mass of fuel. And for this purpose, chemists define the term as the kilogram calorific value, and it's just the heat produced when 1 kilogram of a fuel is completely burned in excess oxygen. Almost the exact same thing as the heat of combustion, however, it's just when we're talking about mass as opposed to number of moles. This table here has the kilogram calorific values of some of the major fuels, and I'm hoping you can notice that they're the exact same fuels where we had a look at the heat of combustion. And now the table, it's skewed a little bit. So as you can see now, hydrogen, even though it gave out the least amount in terms of heat of combustion, it gives out the most amount in terms of kilogram calorific value. So if you're talking about a kilogram, hydrogen definitely gives out the most energy. However, if you're talking about heat of combustion in terms of kilojoule per mole, hydrogen will give out the least. So it's just interesting to compare the two and see the difference in them. Okay, just to note, the kilogram calorific values can be calculated from the heats of combustions for fuels, but it has to be fuels that have definite chemical formulas, so something like methane and butane or pentane, whatever it might be. This calculation is carried out by dividing the heat of combustion by the relative molecular mass. That gives the heat given out when 1 gram of the compound is burned, and then you multiply that value by 1,000 to give the kilogram calorific value. Now, you don't need to know that calculation for your Leaving Cert exam, like you won't need to know the formula for it. However, they could in question 6 when they're talking about it, tell you about this and get you to answer questions on it. So it's just trying to let you see the different types of questions that could be asked or the different types of things that they could put on the exam, so that when you come into the exam, you're not freaking out when you see something that you haven't seen before. Now, so the use of kilogram calorific values, the main thing is they help us compare the efficiencies of fuels. Now, you would have seen on the previous slide, I had a few values, and you could have seen that hydrogen is quite a high kilogram calorific value, and so does methane. You should note when you're studying fuels that methane itself is an excellent fuel. One, as we said already, it has a high kilogram calorific value, but it's also quite clean. It can be easily distributed in pipes to homes, and it's kind of made quite easily. So it's one to kind of watch out for. It could come up on the exam and they just talk about methane, but that's more in the fuel section than it would be in the thermochemistry section. The final thing to note about kilogram calorific values is when you have a substance that has a variable composition. So for example, something like petrol or coal or peat, the kilogram calorific values have to be measured by a bomb calorimeter. You can't use the method where you take their heat of combustion divided by the relative molecular mass and multiply it by 1,000. The reason why we can't use this method is because they're not pure substances. So the relative molecular masses change depending on how pure and the quality, I suppose, and the composition of the particular fuel that we have. So be it coal maybe, or petrol or peat. On an exam, if you're given the kilogram calorific value for maybe one of those fuels, it'll always be given as an approximation as well. It'll never be given as a definite value. Now, looking back at what we've done in the last few slides, so we've defined what the heat of combustion is. We have discussed the combustion of hydrocarbons. We've recalled the use of the bomb calorimeter. We've recalled the heats of combustion of different fuels. We should now be able to define the kilogram calorific value, and we should be able to recall the use of the kilogram calorific values as well. Now we're kind of moving into the final section here of thermochemistry. So now we're going to have to be able to define what bond energy is. We're going to illustrate bond energies by showing the CH bond in methane is calculated. We're going to define heat of formation. We're going to define law of conservation of energy, which you should know already. We're going to define Hess's law. We're going to be able to calculate the heat of reaction and calculate the heat of formation too. Okay, so the first thing we're going to look at is bond energy. Now, bond energy is kind of the idea of what determines the value of our delta H, or our heat of reaction, for some type of particular reaction. Now, if we consider the combustion of methane to begin with, which I have here, so that's CH4 with oxygen, and again, anytime you have the combustion of hydrocarbon, which is just carbon and hydrogen, you're always going to form carbon dioxide and water. Now, as you should already know, when a chemical bond or when a chemical reaction occurs, bonds are broken and new bonds are formed. Now, energy is required to break a bond, and energy is released when a bond is formed. So if we examine the left-hand side of the above equation, we see that 4 CH4 bonds and 2 O2 bonds. So there's a bond between the carbon and the 4 hydrogen. So that's 4 bonds in total with the CH4. And we have 2 oxygen molecules, so 2 O2s. So that means there's a double bond between each of the oxygens. So there's 2 oxygen molecules, each having an oxygen bonded to an oxygen by a double bond. Now, the energy involved in breaking bonds is called the bond energy. And here we define bond energy as the average energy required to break 1 mole of a particular covalent bond and to separate the neutral atoms completely from each other. Bond energies, or their values, are measured from studying the spectra of molecules and also from the heats of reaction. They were used by Linus Pauling to draw the electronegativity values, which you would have looked at when you were looking at electronegativity. And on the next slide, I just have some average bond energy values. Okay, here I have the average energies for different types of bonds. We have a carbon-hydrogen single, a carbon-carbon single, a carbon-carbon double, an oxygen-hydrogen single, an oxygen-oxygen double, and a carbon-oxygen double. Now, the value for delta H, or the heat of reaction, for a particular reaction is dependent on the amount of energy that is needed to break the bonds and the amount of energy that is liberated when the new bonds are formed. So these are really, really important. And in the next slide, we're just going to look at the key term of average. So like why, for example, do I have average here? Why is it not just a set value? Okay, the reason that the bond energies in the last slide are averages is because it's found that the bond energy for a particular bond can vary. So for example, the energy to break the first CH bond in methane is not the same as required to break any of the other CH bonds. So it's just an average of all of the bond breaking required for a CH bond. Another heat of reaction that we're going to be looking at is heat of formation. Now, heat of formation is defined as the heat change that takes place when 1 mole of a compound in its standard state is formed from the elements in their standard states. The key word in that definition, I think, is standard state. And the standard state of an element or of a compound is its normal form at 25 degrees and 101 kilopascals. Now, the main thing to note there is that is normal atmospheric pressure. And it's really important not to confuse that temperature with the standard temperature that you would have looked at when you were looking at properties of gases. So obviously standard temperature is 273 Kelvin or 0 degrees Celsius. Just to make sure that you're fully understand what standard state means. So if we take oxygen, for example, it's going to be a gas at 25 degrees and 101 kilopascals. If we look at maybe magnesium, that's going to be a solid at 25 degrees and 101 kilopascals. And if we look at water, for example, that is a liquid, obviously, at 25 degrees and 101 kilopascals. It's really important that you know how to pick out the correct equation for the heat of formation of any substance. Here I have 3 equations for the heat of formation of water, and we're going to have a look to see which one is the correct one. So if we look at the first one here, we have 2H2 going to O2 going to 2H2O. Now, H2 is gaseous, O2 is gaseous, and water is gaseous as well. Now, you should hopefully be able to spot that this is not the heat of formation of water, and the reason why is because it shows the heat change when 2 moles of water are formed from its elements, and the definition states that it needs to be 1 mole. The second equation then is H2 plus half O2 goes to H2O. Now, H2 is gaseous, O2 is gaseous, and H2O is gaseous. Now, it's much better than the first equation because we have 1 mole of hydrogen been formed. However, it also does not represent the heat of formation of water, because the water formed in this second equation is in the gaseous state. Now, at 25 degrees, the normal state of water is liquid. Therefore, it doesn't meet the criteria for the definition of the heat of formation. The third equation we have then is H2 plus half O2 goes to H2O, where H2 is in the gaseous, O2 is in the gaseous, and H2O is in the liquid. Now, the heat of formation for here is correct, and the reason why, if we look at the definition, it's the heat change that takes place when 1 mole, and we have 1 in front of, or it's 1 molecule of H2O, is in its standard state, so it is liquid, and it's from their elements in the standard state. So hydrogen H2 is gaseous and oxygen O2 is also gaseous. So this one is the correct equation for the heat of formation of water. The next thing you need to know is Hess's law. Now, Hess's law was proposed by a Swiss-Russian chemist, Hess, who was a professor of chemistry at the University of St. Petersburg in Russia. What he was doing was he was studying the heat changes involved in loads of different chemical reactions. He found that the quantity of heat produced in going from one substance to another was the same no matter what route was taken. And this is what he came up with. And he said if a chemical reaction takes place in a number of stages, the sum of heat changes in the separate stages is equal to the heat change if the reaction is carried out in one stage. So, in other words, the amount of heat liberated or absorbed in a chemical reaction is the same whether the reaction takes place in one step or in several steps. Hess's law is really just a restatement of the more general law of conservation of energy as applied to heat changes involved in chemical reactions, where energy cannot be created or destroyed but can only be converted from one form into another. The usefulness of Hess's law is that it allows thermochemical equations to be added, subtracted, multiplied, or divided to calculate unknown heats of reaction. And for this reason, it's one of the most useful laws in thermochemistry, and we're going to be using it now in a few minutes. There are two types of Hess's law calculation on the Leaving Certificate Chemistry exam, and I'm going to go through now in the next few slides the two types of calculations. The main thing is that you're going to follow the method that I'm going to show you every single time. If you don't follow this method, what can happen is you can end up going around in circles, you can start making mistakes. However, they're very simple and easy calculations, so once you have the method nailed down, the rest of it will be really, really simple. Any question that comes up, you should be able to see it, go, yes, I know how to do this, and move forward straight away. The first type of one that we're going to look at is calculating the heat of formation. Now, there's 4 steps. Step 1 is you write down the equation you're looking for. Step 2, you write down the equations that are needed. Step 3, you rearrange the equations needed so the reactants and products are on the same side as in the equation you're looking for. And step 4, you cancel out the reactants and products in the rearranged equations and you will get the equation that you're looking for. Now, fully understand that right now you've no idea what any of those 4 steps are. However, we will go through them in detail now. On the PowerPoint here, I'm going to go through one example of each type of calculation, so of Hess's law. So the first one is the heat of formation and the second one is the heat of reaction. Now, to begin with here, I'm going to look at the heat of formation, and this example is the exact sample that's on your booklet there, and it's example number 1 where it asks you to calculate the heat of formation of methane from the following data. Now, it tells us here we have the heat of formation of carbon dioxide and we have the heat of formation of H2O, water. And then we also have the combustion of methane, which is the third equation. So I'm going to follow each of the 4 steps on the next few slides, and with me, you should be able to calculate the heat of formation of methane really, really simply. Okay, so step number 1 is you write down the equation you're looking for. Here, we're looking for the heat of formation of methane. Now, you need to be able to write the heat of formation of different compounds that you'll be coming into contact with, and this one here, methane, CH4, you should know that it's a gaseous compound, and then it's obviously made of carbon and it's made of hydrogen, so you just write carbon plus hydrogen and then balance it out. So hydrogen is always H2, oxygen is always O2. After that you should probably be fine. So the heat of formation, then we've written it down, and then we need to figure out what this value is. In step 2, you write down the equations needed. Now, the equations needed in this case are given to us, which is quite handy. We have the 3 of them here, and that's all you need to do. And you need to write that down directly underneath where you've written the equation that you're looking for. Step 3 then is you need to rearrange the equations so that the reactants and products are on the same side as the equation you're looking for. Now, I've kind of done it all in the one step here, but when I'm going through an exam question, you'll see exactly how we do it. So to begin here, we have carbon on the left-hand side, so we need carbon on the left-hand side. So we go to the 3 equations that are given to us, and we make sure that carbon is on the left-hand side. And you can see here, I've matched it up. It is on the left-hand side, so it's fine. So this one is grand. We don't need to do anything to the top line at all. The second one then is hydrogen, which is H2. That needs to be on the left-hand side, and here it is on the left-hand side. However, if you look, it's 2H2, and we've only got 1 H2 here. So what we need to do is we need to multiply the entire second line by 2. The last one there, we have the combustion of methane, and that means that CH4 is on the left-hand side. However, we need CH4 to be on the right-hand side. So what we do is we're just going to flip this around, turn them all around like so. So when we apply those changes, the top line stays exactly the same. The second line here is multiplied by 2, and you need to also make sure that you multiply the delta H by 2 as well. Last line then, we have the CH4, it's now flipped over to this side, and the only thing we have to do when we're flipping it over is making sure we change the sign, because it's the opposite way around, so the heat has been taken in as opposed to being given out. The final thing we do then is we put a line underneath all of what we've done so far. And what we do is we add together the three equations that we've now created. So we have a carbon, which comes down here. We've 2 oxygen on the left hand side, but we've 2 oxygen here on the right hand side. So they're going to cancel out. We have a CO2 here on the right hand side, but we also have a CO2 here on the left hand side. So that will also cancel out. We have a H2O on the left hand side here and a H2O on the right hand side here. They will cancel out, so you won't need to write those down. And then the only thing we're left with then is the methane, which is the CH4. Now, then what you do is you just write those ones down. So we have carbon plus 2H2 goes to CH4, and then you add all of your delta H values, and we get delta H equals minus 86 kilojoule per mole. Now, we always know if we're right in these equations or in these questions, because the bottom line here, what we're left with at the end, will always match the one at the top. And if you see here, they match perfectly, and we've now figured out what that question mark is. It's minus 86. The second type of question they can ask you to answer on Hess's law is calculating the heat of reaction. Now again, there's 4 steps involved here, so they're the exact same as the last time. You write down, first of all, the equation you're looking for in step 1. You write down the equations needed in step 2. For step 3, you rearrange the equations needed so the reactants and products are on the same side. And in step 4, you cancel the reactants and products in the rearranged equations, and you will get the equation you're looking for. The second type of calculation you can be asked to do then is calculating the heat of reaction. Now this example I'm going to go through here is exactly the same as example 3 that's in your booklet, and it says here calculate the heat of reaction of the following reaction, and we have 2H2S plus SO2 goes to 3S plus 2H2O. Now again, we're going to follow the 4 steps, and I'm going to go through the 4 steps in the next slide. Okay, so now remember, in step number 1, you write down the equation that you're looking for. And the equation that you're looking for is the one that they gave us in the question, and the delta H is the unknown. Step number 2 is you write down the equations that are needed, and those are the equations that are given to us in the question. Now, the answers for step number 3 will be on the next slide, but I'm going to show you how you go about doing it here in step number 2. So step 3 is we rearrange the equations needed so the reactants and the products are on the same side as the equation that you're looking for. So to begin here, we need 2H2S on the left hand side. Now at the moment, if you can see here, we have H2S on this side, and it's only 1 as well. So what we have to do here is we flip this guy around. It's going to have to be changed around, and it's also going to have to be multiplied by 2. Looking at the next one then, we have SO2 here on the top left, and we have SO2 in the second equation, but it's on the right hand side. So again, we're going to have to flip that over. Now, thankfully in this one, we don't have to multiply it by any number because it's 1 SO2 and it's 1 SO2 that we have as well. Next then, we need 3 sulfur here on the right hand side. At the moment, we have 1, 2 sulfur here. However, we are going to multiply this by 2, so it's not too bad. And also we're going to flip both of them, so they're also going to be on the correct side. So when we multiply the top one by 2, we'll have 2S and we'll have 1S. So that'll give us 3S, but they need to be on the other side, but we're already flipping these equations, so it's okay. Lastly, then we need 2H2O, and we have H2O here. It's on the correct side, but we do need the 2 in front of it. So we're going to have to multiply this line by 2. Now, when we do that then, so again, we're multiplying the top one by 2 and flipping it around, or flipping around the second one, and we're multiplying the bottom line by 2. So when we do that, we end up with these guys down here. And now remember, step 4 is we cancel out the reactants and the products in the rearranged equations, and you will get the equation that you're looking for. So just to show you that, so first of all, we have the 2H2S, so I'm going to write that here, so 2H2S, that's grand. And then we have the SO2 on the left hand side. Now down here at the bottom we have 2H2, so technically we would need to write that down because it is there. However, if we look on the other side of the equation, we have 2H2 here, which will cancel out with the 2H2 up here. Next we have the O2, and we have 1 O2, and up here that will cancel out with the 1 O2 that's on the right-hand side. Finally then, we just write the right-hand side of the equation. So we have 2s in the first line and 1s in the second line. So we add them together, that will give us 3s. And then we also have plus 2H2O. Finally, just make sure you put in your the states that they're in. So we've gaseous, solid, and then we have gaseous here. Finally, the last thing we need to do is we need to add up all the delta H's, but I have that nicely written on the next slide. So as you can see, they all match up, they all cross out, and we get the equation. And how we know we're right is if we look up here at the top, this is the equation that we were given in the question. This is the equation that we ended up with at the end. Because these match, we know they're the exact same. Then, just to remind you, we always need to get the delta H. That's what the question is all about. So we add up these guys and we'll get plus 53 kilojoules per mole. Okay, looking back what we've done on the last few slides then. So we've defined bond energy. We've illustrated bond energies by showing how the CH bond in methane is calculated. We've defined heat of formation. We've recalled the law of conservation of energy. We've defined Hess's law. We've calculated the heat of reaction and also the heat of formation. So what I'm going to do now is I'm going to go through a few exam questions, have a look at them kind of by a sample kind of test that I've put together. I'll go through a few more of the heat of reaction and heat of formation calculations. Okay, so as I said in the previous slide, I'm going to go through here maybe a sample test. These are all past exam questions. I've just collated them into one place. So this test is out of 75, so it should take maybe 30 minutes-ish to do. However, we're going to look here and we're going to work through it together. There's a lot of definitions in here, and just to remind you, in the little booklet that you have for thermochemistry, at the very last page, there is all the definitions that you're going to need to know for thermochemistry. It also says exactly how often these definitions come up. And the first one, heat of reaction, has only come up twice. Now, it is just the heat change when the number of moles of the reactants indicated in the balanced equation for the reaction react completely. Unfortunately, you need to know that off by heart, and there's no easy way of doing it. You just need to understand what heat of reaction is, and on the day of the exam, just write it down. Okay, so part B then, it says the combustion of 2,2,4-trimethylpentane may be described by the following balanced equation. And you should have done fuels before this, so you should know that 2,2,4-trimethylpentane is a reference hydrocarbon that's used to denote octane number. Now, the octane number of 2,2,4-trimethylpentane is 100. Okay, so this question then asks us to calculate the heat of combustion of 2,2,4-trimethylpentane, given that the heats of formation of 2,2,4-trimethylpentane, carbon dioxide and water, are minus 259, minus 394 and minus 286 kilojoules per mole respectively. Now, so this is calculating the heat of combustion, which is the same things as heat of reaction, because obviously a combustion is just reaction. And we follow the 4 steps as we do every time. And it says here, write down the equation that you're looking for in step number 1. And that's what I'm going to do over here on the right-hand side. So we're doing part B. And to begin with on part B, we're going to write down the equation we're looking for. The equation we're looking for there is the one they've given us. So we have 2C8H18 plus 25O2. That's going to go to 16CO2 and 18H2O. Now, and then the delta H value for that is the question mark. That's what we're trying to find out. Okay, now the second step we have to do then is write down the equations needed. And they've given us the equations that we need here in the sense of like what we're going to have to come up with. And it says the heat of formation of 2,2,4-trimethylpentane, carbon dioxide and water. So we'll start with the 2,2,4-trimethylpentane. Now, 2,2,4-trimethylpentane is the one here. So it's C8H18. So that's just made of hydrogen and it's made of carbon. Carbon is just C, hydrogen is H2. So to make this balance then, we just need 8 carbons. And in total, we're going to need 18 H's, but we have H2 here to begin with. So that's going to mean that we're going to need 9 H2 up here. Last thing we need to do then is just write the delta H value for this guy. And the delta H for this reaction is minus 259, and then it's kilojoules per mole. The second one we have then is of carbon dioxide, and carbon dioxide is CO2. That's again going to be carbon, except this time we're going to have O2. Now, thankfully, we don't need to do anything to those because 1C plus 1O2 gives us CO2. And finally, the H for this reaction is minus 394 kilojoules per mole. Okay, then the last one we have is water. Now, water is H2O. To form water, we're going to need O2 and we're going to need H2. Now we'll have half O2 to give us the 1O, and we need 1 H2. So the delta H for this value is minus 286 and then kilojoules per mole. Now that's step 2 done. We've written down the equations needed. Step 3 is we're going to have to rewrite or rearrange the equations needed so the reactants and products are on the same side as the equation you're looking for. So to begin with here, we need 2C8H18. At the moment we have the C8H18 here, so it needs to be flipped over to the other side to begin with. And we also are going to need to multiply it by 2 because we need it to be 2C8H18. We're going to leave the oxygen for the minute, so the oxygen that's here, and we'll go straight to the carbon dioxide. The carbon dioxide, we need it to be on the right hand side, but we need 16 of them. So we're going to multiply the second line by 16. And then on the final line, we need 18H2O on the other side, or on the right hand side. And that's on the right hand side at the moment, which is grand, but we've only got one, so we need to multiply by 18. Now, so we're going to write them out then change. So the first thing is the top equation is going to become 2C8H18. And then that's going to go to, and we'll have 16 carbon and 18 hydrogen. Now, the delta H value for that reaction then, to figure out what it is, well, first of all, we're flipping it around, so it's going to change the sign. But then otherwise, we need to then multiply it by 2. So you go 259 multiplied by 2, and that's going to give you 518. And again, kilojoules per mole. The second equation then, we're multiplying by 16. So we'll have 16 carbon here plus 16 O2. That's going to give us 16 CO2. And then the delta H value for that equation is, well, it's minus 394. And that minus 394, you need to multiply by 16. And when you do that, you'll get minus 6304 kilojoules per mole. Last equation then, you're multiplying by 18. So on the left-hand side, we'll end up with 18H2 plus 9O2. And that's going to go to 18H2O. Now, the delta H value for that guy then, so again, we have minus 286, and you need to multiply that minus 286 by 18, and when you do that, you're going to get minus 5148, and then that's kilojoule per mole. Okay, so if we're looking back where we are in terms of steps, now we have step 1, 2, and 3 done. We now need to figure out what the answer is going to be, so we're on step 4. So what we do is we put a line underneath, and we cancel out the reactants and the products in the rearranged equations, and hopefully, if we've done everything correct, we'll get the same equation that we had at the start. So we begin by just writing down what we have. So it's 2C8H18. So we've got that one done, that one's ticked off. Now next then on the left hand side, so we've 16 carbon, but if you see here, we've 16 carbon here and we've 16 carbon here, so those guys will cancel out. Next then, we have 16 O2, but we also have an O2 underneath it, so we've 9 O2. So when you add them together, you're going to get that is 25 O2. On the bottom line then here, we have 18 H2, but up here on the top right hand side, we have 18 H2 as well. So those guys will cancel out. Then seeing what we've left on the right hand side, we have, well, we've 16 CO2 and we have 18 H2O. So if we compare that with what we have at the start, so we have 2C8H18, 2C8H18, 25O2, 25O2, 16CO2, 16CO2, 18H2O, 18H2O, and then we just need to calculate what the delta H value is going to be. To do that, all you have to do is add up the delta H values that we have here on the right hand side. So we start with the 518, then we have minus 6,304, and we have minus 5,148. So the delta H value that we get here then is minus 10,934 kilojoules per mole. Right, going back then and looking at what we're actually doing here. So it says calculate the heat of combustion. Now, if we go back and we just make sure that we have the heat of combustion correct, the heat of combustion definition says it's the heat change when 1 mole of a substance is completely burned in excess oxygen. And if we look here, we're looking for 1 mole and we have 2. So all we need to do at the end here is, because we're looking for 1 mole, is take that minus 10,934
and divided by 2. That will give us the heat of formation of just 1 mole of the substance. So we end up with 5,467 kilojoules per mole. And that is question or part B of this question done. Now, this will always be on the exam. It's been on the exam since the Leaving Certificate Chemistry course has started. It's always question 6. And if you know how to do this method, it'll make it much easier. Now, then going back and looking at part C, it says define the heat of combustion. Now, we've just looked at that again. It's a definition that you need to know off by heart. It's in your booklet. It's the very last page, and it is the heat change when 1 mole of a substance is completely burned in XX oxygen. For part D here, it says name the piece of equipment used to measure the heats of combustion of different substances. That's just your bomb calorimeter. The final part here, part E, it says write a balanced equation for the combustion of methanol, which is CH3OH. Now, you should remember again that the combustion of any hydrocarbon gives us carbon dioxide and water, and it's the same for a fuel. So, for example, here where we have CH3OH, we're going to combust that, so it's going to be reacting with excess oxygen, and it's going to form carbon dioxide and water. Then we just need to balance. So on the left-hand side, we have 1 carbon, and on the right-hand side, we have 1 carbon. That's perfect. In terms of oxygens here, we have 1 and then 2 here. So that's 3 in total on the left, and we have 3 in total on the right. And then if we look at hydrogens, so we have 4 here on the left, we've 2 here on the right, so that means we need to put a 2 in front of this guy here to make it 2. That skews up our oxygens a little bit, so we'll go back and look at the oxygens. So we have on the left hand side, we're going to have 3 oxygens here. On the right hand side, we now have 2 and 2, so we'll have 4. So we're just going to need 1.5 of these guys to make it balance out or make it equal. Okay, so there's some questions that could be asked on an exam. It could be question 6 on thermochemistry. On the next slide, I'm going to go to another sample exam question. Okay, so this is just another example of the type of question that you need to know for thermochemistry. It is a past exam question, and in particular, this one is focusing first of all on defining the heat of formation. Heat of formation is just a definition that you need to know. All the definitions are at the back of your little booklet that accompanies this video. And heat of formation is the heat change that takes place when 1 mole of a compound in its standard state is formed from its element in their standard state. Again, it's a definition, you just have to learn it off and write it down. In part B, it says ethene is prepared by the dehydration of ethanol using the dehydrating agent aluminium oxide according to the following balanced equation. And now you should be quite familiar with that if you've done fuels already, because you prepare ethene in fuels, and that's the chemical equation for it. It says here, calculate the change for the reaction given the heats of formation of ethanol, ethene and water are minus 278 plus 52.3 and minus 287 kilojoules per mole respectively. Very similar to the last time, this is a heat of reaction question. So to begin, we're going to follow our 4 steps. Step number 1 is you write down the equation that you're looking for. And here we're looking for the heat change from the reaction that they've given us there. So the reaction is C2H5OH going to C2H4 plus H2O. Now, that's the equation that we're looking for. Next, we have to write down the equations needed. And here we need, where they've kind of given us as well, we need ethanol, we need ethene, and we need water. And the heats of formation of those guys are given. So, ethanol is C2H5OH. We have ethene, which is C2H4. And we have water, which is H2O. Now, the delta H of these guys as well, we can write down. So, it's minus 287. Okay, now, all of these guys have been formed and we basically just look at what's involved in it and we write down. So to begin with here, we have carbon, we have hydrogen, which is always going to be H2, and we have an oxygen, which is always going to be O2. So we need 2 carbons to form it. We need 6 H2, so that means we're going to need 3 H2 here, and we're going to need a half O2. For ethene, it's going to be C and it's going to be plus H2. We're going to need 2 carbons and we're going to need 2 H2. And for H2O, well, it's H2 and then we'll need a half O2. Okay, so that's step 2. We've written down the equations needed. Now in step 3, we're going to rearrange the equations needed so the reactants and products are on the same side as in the equation you're looking for. So we'll start here with the C2H5OH. That's on the right hand side up here. We need it to be on the left hand side. So for this one, what we're going to do is we're going to flip this guy around. But otherwise, the number in front of it is fine the way it is. For the next one then, for C2H4, it needs to be on the right, and it is on the right, and we need it to be 1 C2H4, and it is 1 C2H4, so that's perfectly fine the way it is. And for the third one, it's also grand the way it is too, because we have the H2O on the right-hand side, and it is on the right-hand side in the equations that we have, so both of these guys can stay exactly as they are. Now, we'll flip that guy around, the top guy, and we'll be left with C2H5OH. That then is going to go to 2 carbons plus 3 hydrogens plus half oxygen. And the delta H of this guy now, because it's been flipped around, is going to change. So it'll be 278 kilojoules per mole. And we'll forget about the minus because it's in the opposite direction. Second and third equation then stay exactly the way they are. So we can leave them. Okay, now step number 4 then on this, it says that we need to cancel the reactants and products in the rearranged equations, and you will get the equation you're looking for if all is done well. So we pop a line underneath here. I'm going to change my colour now to red, and I'm going to add them up. So to begin with, we have the C2H5OH on the left hand side, and that's perfect. Then we have the 2 carbon here, but we do have a 2 carbon on this side, so those will cancel out. So we'll have these guys cancelling. Next then we have 2H2 and H2 here, so that's 3H2 in total, and we have a 3H2 here, so they'll cancel out. And then last we have half O2, and we have a half O2 up here, so that will also cancel out. So that's actually all of the left hand side done. Looking at the right hand side, nothing is remaining on the top line, but on the second line we have C2H4 and we have H2O. Now, so if we check to see to make sure we have it correct, so we've C2H5OH and we've C2H5OH, C2H4, C2H4, H2O and H2O here. Then we just need to calculate the delta H, and again to do that we just need to add the numbers that are on the second set that we have here. So we start with 287 and then we're going to have to plus 52.8 to that, and then take away 286. And when we do that, we'll be left with 44.8 kilojoules per mole. Okay, so if we go back and just make sure we don't need to do anything, we don't need to divide by any numbers or anything like that, it says ethene is prepared by the dehydration of ethanol using the dehydrating agent aluminium oxide according to the following equation. That's grand. It says calculate the heat change. So we're not calculating the heat of formation or the heat of combustion, so we don't need to be too cautious about 1 mole of a substance and in its standard state. So the way we have it here is perfect. It's the heat change for the entire reaction. We've been given the reaction, we've calculated the heat change. Okay, so now we've come to the end of this video, or this section of the revision course, just to go through a few things on your booklet. So I'm hoping you got all of the blanks filled in the theory part of the booklet okay. It's all on this PowerPoint, so go back on the video and just kind of pause and stop wherever you need. There is loads of examples of heat of formation and heat of reaction calculations. I know I've only gone through 4, but they're all the exact same. So if you keep following the same steps that I've done here, you should be able to do all of them absolutely no problem at all. So I hope you find the questions in the booklet okay, and if you don't, just get in touch and I can help you as much as possible. The other thing to note, just at the very start of the booklet that goes with this video, there is the combustion of hydrocarbons. Now, the reason why I put that in here is because we were kind of looking at it in the sense of heat of combustion, and it is a little bit of revision from fuels. So the whole idea there was just that hydrocarbons themselves burn in air to form carbon dioxide and water, and the carbon atoms in the hydrocarbon are oxidized to carbon dioxide, and the hydrogen atoms are oxidized to water. So I can go through those 3 examples really quickly here. So the first one, it says write a balanced equation for the combustion of ethine in excess oxygen. Now you should know this from when you were studying fuels and when you were creating ethine. Ethine is C2H2 Anytime you have a hydrocarbon and you combust it, you're just reacting it with oxygen and forming carbon dioxide and water. So this is the equation. The last thing you'll just need to do is just balance it. So we've 2 carbons on the left, so we're going to need 2 carbons on the right. We have 2 hydrogens on the left, so we need 2 hydrogens on the right, and we do. Then in terms of oxygens, we have 2 on the left, and here we have 5 on the right. So we are going to need 5 over 2, or 2.5 on the left hand side. The second one then, it says the balance equation for the combustion of butane and XX oxygen. Now you should know that butane is C4H10. When that combusts, it's going to give you CO2 and it's going to give you H2O. Now again, it's oxygen that it's going to combust with, and then we just need to balance. So we've 4 carbons here on the left, we need 4 on the right. We've 10 hydrogens then, and we only have 2 on the right, so we're going to need 5 here. Then looking at the oxygen, so we have 4 times 2, which will give us 8, plus 5, so we have 13 here on that side. So we're going to need 13 over 2 on the left, and 13 over 2, of course, will give you 6.5 oxygens on the left hand side. Okay, the final one then that you have on page 2 of the booklet there is write a balanced equation for the combustion of ethene. Now ethene is C2H4, and again it's just combustion, so it's going to be reacting with oxygen and it's going to form carbon dioxide and water. Looking at ethene, you should know this from when you were creating ethene, but we've 2 carbons, so we need 2 carbons here. We've 4 hydrogens, so we need 2 here. So that means we'll have 4 hydrogens here and 2 hydrogens here, so we'll have 6 in total, so we'll need 3 with the oxygen. So that's just going over one more time the combustion of hydrocarbons as such. And again, if you have any questions on that, it's the fuels kind of section of the course that's in. It does usually come up with thermochemistry as well, so that's why I kind of included it here just at the end and also in your booklets.